Welcome back, everyone. Our next presenter, Dr. Marcus Ross, earned his PhD in geosciences from the University of Rhode Island. He served as professor of geology at Liberty University until a few years ago, and also as the director for their Center for Creation Studies. He is the founder and CEO of Cornerstone Educational Supply. He continues his relationship with Liberty University, and he is published widely and spoken widely on issues related to creation. So it's my pleasure to turn things over to Dr. Ross.
Thank you very much, Gary. It is a delight to join the Society for Creation here for this conference. I'm grateful for the opportunity to join you guys, and very excited about the presentations, both that I get to provide as well as the ones that I get to hear from you and the other presenters this year. So grace and peace to you and all those who are watching from me here in Lynchburg, Virginia. As mentioned, I am Dr. Marcus Ross. My background is in paleontology. I am a fossils and rocks guy, so to speak. And my own background was primarily in the area of vertebrate paleontology. I studied animals with backbones, studied dinosaurs, for example, and primarily in my PhD, worked upon the animals known as mosasaurs. Those are the giant swimming marine reptiles. Technically, those are, in fact, lizards. Dinosaurs are not, but the mosasaurs were lizards, and they grew anywhere from 10 to over 50 feet in length and ate pretty much whatever they wanted. So I'm very grateful to God that they're all dead. Make going to the beach a very hazardous situation. I was brought into the arena of dealing with questions of human origins through a rather circuitous route. This wasn't an area that I had much interest in earlier on. I was always more interested in things that had lots of scales and teeth. But nonetheless, through a series of interesting events, I was eventually asked to contribute to a multiple views book that is forthcoming, should be published in January of 2024, in which I interact with several other authors, each presenting our own case and interacting with each other. Dr. William Wayne Craig is one of the authors there, as is Dr. Andrew Loke and Dr. Kenton Sparks, all representing different varieties of theistic evolution. And one of the tasks that I had in the paper that I presented is to put the hominid, that is the human ape fossil record, into context for my readers. And so one of the things that I want to be able to share with you all today is how it is that we as young Earth creationists look at this particular record of fossil organisms, both human and non-human, and why it is that most young Earth creationists throughout time, and even virtually all to the present, believe that the human fossil record is primarily one of the post-flood world. Now, before I get any further, I was asked if I might introduce a little bit about Cornerstone Educational Supply, the company that my wife and I founded back in 2015. We started going full-time, and outside of Liberty University, I stepped down in 2021 to helm the company. And you can see our website, for example, at cornerstone-edsupply.com. My wife likes to say we're the stuff people. Whenever your science curriculum is saying, hey, go get some stuff to do some things for science, that's our business. We're interested in being able to provide the laboratory and science equipment in order to do different sort of work, whether you are in a private Christian school or a public school, college or university, or homeschoolers. We have materials available for a wide variety of different aspects of science. I got started in geology because that's my area, and I wanted to create geology kits that had as many or more specimens than the types of kits that I was using in my college classes. I also wanted them to be a better and more reasonable price. We kind of got gouged. So we started Cornerstone with the aim of getting geology kits, fossil kits, mineral kits, rock kits into the hands of especially Christians, and help them see that there are ways of studying God's world that don't have to come into direct conflict with evolutionary ideas, old Earth geology ideas, but rather can provide a way in which we can approach these disciplines in a way that honors God as the creator of all things, as the judge of all things in the flood, but also his providential care of all things subsequently. So you can find us again on the web at cornerstone-edsupply.com, and we'd be happy to help out with your co-op, your community, your school, or your college classes, and creating customized materials or anything else we can do for you. So on to our discussion here today about the geology of the post-flood world and its context in setting the stage for human migration, for example, in the human fossil record. So over the course of this presentation, we're going to have a few questions that we want to ponder. We're going to be asking a question concerning geology: in which rocks, and particularly which rock layers, are human beings found? So this is a question about those layers out there. And are humans found in all of them, or are they found in some of them? And if so, which ones? We're also going to be asking some questions of geography. Where are the human fossils found? So we have locations geographically, that is the second question, and locations stratigraphically, which is our first set of questions. And so we've got the layers, we have the geography. We need to get these pinned down so that we can address some of the other questions, not only for this talk, but also the others that are coming up during this conference. So taking a look at our first set of questions: in which rocks are humans found? First question from that, actually, that we need to address is whether or not the geological column, that construct of all those different names and layers of Jurassic and Cretaceous, Devonian, and all sorts of different stuff, Ordovician, Paleocene, Eocene, is that a reliable system, or is that just some sort of evolutionary trick to put things in order the way that evolutionists want to? And if it is reliable, or at least generally, what layers of rock are we looking at? Are those flood or post-flood rocks? So, is the geological column reliable? To understand the geological column, we have to step back into the question of relative and radiometric dating. So dating methods in geology follow two large categories. One is referred to as relative dating, dealing with a comparison age, that is a relative age of one layer or unit of rock versus another. Is this rock that I'm looking at here A, older or younger or contemporaneous with B? So we're not using numerical dates when we're talking about relative dating. It's mostly dealing with fossils that are found, and we'll see why in a moment, and the positions of rocks with respect to one another. Another group of evidences or arguments for the age of the Earth comes from radiometric and other what are referred to sometimes as absolute ages, because those are the methods that are supposed to give us an actual numerical age for a particular rock, whether it's measured in hundreds of thousands or millions or billions of years. Radiometric dating is certainly the most well-known and most frequently applied. There are a few others as well. When thinking about radiometric dating, this uses the decay of radioactive materials as a stopwatch of a sort. There are certain types of materials, such as carbon or uranium. Carbon-14 is radioactive, carbon-12 is not. All forms of uranium are radioactive. So when we're looking at radioactive materials, we have to know what those are. And we have to ask the question, do we know how fast they decay? And then use ratios of what is there versus what the decay products are in order to come to a particular date. So that is, on the quick level, how radiometric dating is used. It's trying to take a look to see how much time has elapsed because of the radioactive decay of other materials. So here we have a geological column. This is a representation of the geology of the world according to various units of time. And these units of time are divided and given names. We'll focus ourselves here at first down the middle of the column. And I'll bring my laser pointer here. We look down the center. All of these names, Precambrian and Phanerozoic, Paleozoic, Mesozoic and Cenozoic, Cretaceous, Jurassic, Triassic, all the names within here are names that have been assigned and given to different rocks. on the basis of either their fossil content and relative positions to one another, or by radiometric dating. Important to note is that the construct of the geological column was actually built long before any of the numerical ages were applied to it. In fact, it was also built prior to the development of evolutionary theory. When Darwin wrote The Origin of Species and published it in 1859, he was using a geological column that was relatively complete, missing only a few pieces of what we have here today. For example, at his time of writing, the Silurian occupied what we would now consider both the Silurian and the Ordovician. The Ordovician was not codified as something separate yet, and eventually it would be. But still, the Ordovician is located in what would have been referred to then as the Lower Silurian. Likewise, the Paleocene up over here would not be recognized until deposits in North America showed that there were material that was older than the Eocene assemblage of fossils and younger than the Cretaceous ones. So that got sandwiched in between because of different fossil materials. So when Darwin was writing The Origin of Species, he didn't create the geological column. Far from it. He was already using it and was taught it by his own geology professors in the early 1800s. Darwin simply presented evolution as an explanation for the particular pattern of the rocks and the certain types of fossils that are found in them. That is found here in this column of notable fossils, for example. This is certainly not exhaustive. For example, dinosaurs are known in the Triassic, the Jurassic, and Cretaceous rocks. They're part of the sorts of fossils that are characteristic of these units and are not found in rocks below, for example, nor are they found in rocks above. The actual numerical dates would certainly be assigned in the 1800s, but the idea that the Earth was several billions of years old would not be codified until the 20th century with the development of radioisotopic dating methods, or radioactive dating. Now, on the right side of this is a way to possibly understand the geological column from a young Earth creationist perspective. So on the left, we have something like an old Earth or an evolutionary perspective on the ages and dates here. On the right, we have a young Earth creation perspective that would recognize that certain categories of rocks, such as much of the Precambrian, would have been formed during Creation Week and possibly during some of the pre-flood period. Then, at the initiation of the flood, the majority of our densely fossil-bearing units, the ones that have complex life forms, such as trilobites, brachiopods, dinosaurs, various other types of animals, would have been destroyed and buried in sequence during the period of Noah's flood, lasting somewhat over 1 year. And then at some point, we transition to a point where there are rocks and fossils being formed, but in the post-flood period, with residual geologic catastrophism creating localized systems. So the relative dating methods come primarily from the work of people like Nico Steno. And as you can see the date down here, Steno lived in the middle 1600s. Steno was Danish and was the son of a watchmaker and clockmaker at the time. And he eventually went to the University of Copenhagen, where he wanted to learn to be a surgeon. He was going to be a doctor. But through a series of unfortunate events, there was religious wars happening during this period of time in Europe. Steno was forced to flee eventually after being under siege in Copenhagen for a couple of years, nearly dying of starvation, but he eventually fled after doing a good bit of his studies and went to France and then ultimately to Italy, where he joined the students of Galileo Galilei in what was then the very first ever scientific think tank, founded by Galileo's students. When he was there, he was hired on as a biologist, but he got very interested in the question of fossils, which at the time was a good debate, actually, quite a big debate as to what their nature was. Were fossils the remains of formerly living organisms, which is what Steno believed, or were they simply an interesting mineralogical feature that seemed to mirror in some way biological form, but itself was not, which was a contemporary position. Steno was convinced that fossils were in fact biological, but he had a hard question to answer, and that was, how did they get in the rock? Because after all, a rock is a solid object, and the tooth or the shell of an organism is a solid object, how do you get a solid object into another solid object? And moreover, the tooth or the shell that he saw as a fossil was not identical in composition to the tooth or the shell that he might pick up along the side of the beach as he was walking in Italy. So you had to explain a couple of different hard questions in the 1600s. Why is there a solid object in the rock if it's not a mineral? But minerals are in rocks. And also, why does the composition of this solid object look more like minerals than it does like bone or shell? To answer that question, Steno had to become a geologist, and he started studying the geology of the area around him and came up with certain important principles for interpreting the rocks around him in ways that nobody had done previously. He wanted to place these rocks in sequence, and he used some basic rules published in a long paper short book of 70 pages called his Prodromos, which he promised was just the beginning, just the introduction to a much larger dissertation that he would follow up on. He never quite did, as life took him in different directions. But nonetheless, these 70 pages were a powerhouse of geological thought. Steno recognized that sedimentary rocks, such as sandstones, shales, and limestones, must originally start off as loose sediment that is laid out in a horizontal sheet. Because as he looked at the beaches of Italy, nearby where he was living, he would notice that the beach is made of sand, and that sand is relatively flat. There's a slight angle going out to the ocean, but nonetheless, it's a big sheet of sand spreading out in direction from to the left to the right and out into the ocean. And Steno recognized that if we have sandstone out in the Alps, where he would take some walks, and that sandstone is tilted, it probably didn't start off that way. It originally must have started off as sediment that was laid down flat. This was a key insight, because now Steno is starting to think about rocks in terms of sequence and events, not simply as items that were created there by God. From his first observation of original horizontality came his most important insight into what would become the discipline of stratigraphy and sedimentary geology. This is the idea of what is called superposition. In this case, the word super meaning above. The idea that if all sedimentary rocks start off as horizontal sheets, well, then stacks of them indicate time, because the only way to have stacks of rocks are to have first rocks low, then rocks slightly above, and then more rocks above that. Once Steno could recognize that flat-lying sedimentary rocks would be formed in a vertical sequence over time, he could now start to read different rocks and their orientations as happening more or less recently, closer to the present or deeper to the past. He would also recognize another key insight, and that is what we call the rule of cross-cutting relations. That is, if you have something like a fault that breaks its way through a set of rocks, the fault can only happen after the rocks are already there, because you can't fault nothing, right? No one's at fault. No. If you've got a rock, you can break it. If you don't have a rock, there's nothing to break. So breaks in the rock happen after the rock occurred, and therefore Steno had another tool at his disposal. He could tell whether or not faults or lava tubes were things that had happened before or after other types of geological events. Visually then, we can see this stack of chalks deposited and now exposed along the coast of Norfolk, England. We have an upper unit that is white. We have a lower unit that is rusty red, and a middle unit there that is rusty red, and a lower unit that is white and receiving some rust coloring from the unit above it. And Steno would now look at these, and we can too, that recognize a early, middle, and late sequence for these three groups of rock. Observing the rule of cross-cutting relations, here we have a break, a fault of some kind in between sets of rocks, and we can see that there is this white unit that should go completely across but is offset and higher on the right side than it is on the left, because the fault has displaced the rocks. The rocks have shifted along here. That's how we know it's a fault and not another just simple crack. Some other types of cracks in rocks don't involve movement. But notice, for example, that we have this little white light unit and the brown unit above it. And as they go across and we trace them to the right, they are not offset by this fault. So now, using Steno's principles of original horizontality, superposition, and cross-cutting relationships, we can recognize that there is a sequence of older to younger rocks that are formed here. Then there is a break, and after that, there are new rocks or new sediments that are laid down on top of the old. Without involving any numerical ages, we now have at least a relative understanding of the positions and the sequence of events that must have happened to produce these types of rocks in front of us. We can take this out into the field to other areas. Steno was working in the Alps, but we can take this to the Grand Canyon, and here is a generalized schematic of the Grand Canyon to the south. And going northward into Utah, we pass from Grand Canyon National Park into Zion, and then from Zion into Bryce Canyon. In Grand Canyon, we have the world's largest hole in the ground. It's nearly a mile deep and includes numerous exposed layers of sedimentary rock in sequence. We have the crystalline basement rocks followed by a unconformity. And then we get to, we may or may not have the Grand Canyon supergroup, depends on where you are. You get into the sandstones and shales of the Tapeats, the Bright Angel, the Muav limestone, and so on and so forth. And you can follow these all the way up to, on the north and east side, all the way up to the Chinle Formation, which is Triassic, if I remember correctly. Well, if we go north, we're on a driving tour of the various parks. We get over to Zion, we find that the Chinle Formation is actually one of the lower units of Zion National Park, along with the Moenkopi, Kaibab, and Torweep. The Kaibab is an important rim rock up around the Grand Canyon. You can see Kaibab all over that area. But by the time we get to Zion National Park, we're pretty much standing on top of it. And then there are more and more rocks as we move forward into this area and end Zion with the Cretaceous Dakota Formation. Well, the Dakota Formation is the lowest unit that we have in Bryce, and on up it goes into the Clarion Formation, for example, with a whole bunch of different mammals and whatnot. The quaternary surficial deposits, etc. We can follow the vast majority of the geological record from Grand Canyon through Zion to Bryce Canyon National Park and stop by nearly every single one of those different layers of Cambrian, Ordovician, Silurian, and so forth, all the way up as we go. And so using Steno's principles, we can take a look at someplace like the Grand Canyon and check it against what was done in Europe. And sure enough, it seems that the pattern holds. And this is because, as we've taken a look at fossils in different places, the geological column was primarily built using layers of sedimentary rock that had characteristic fossils in them. If we have two different paleontologists on the left and right here working in different areas, they could be very close, but they could also be very far away. Let's say, for example, that the paleontologist on the right is nearby me in Virginia over into the Shenandoah Valley, and he's excavating a limestone that has characteristic trilobites, and then up above him are some sandstones with ammonites, and above that some shales that have some fish skeletons. Another worker, perhaps over in Ohio or in your area of Wisconsin, might be excavating a sandstone and siltstone that actually has the same trilobites. The rock is different, limestone versus sandstone, but the trilobite is the same. And if they find the same ammonite above that and the same fish skeletons, then it seems that this pattern of fossils found from low to high is correlative from one place to another. We can correlate, we can link the two units on the basis of their fossils, even if the rocks that contain the fossils are rather different. And this is how the geological column was established in England, Germany, France, and other places of Europe initially. They recognized that fossil assemblages could be traced from one place to another, and that the fossils were less variable in some senses than the rocks were. That different rocks could have the same fossils. And so this is referred to as a principle of fossil succession, worked out especially by William Smith in the early 1800s. So what we can say then is that the geological column was established on the basis of patterns of fossils that were found in layered sedimentary rock and then correlated from one place to another. The pattern holds not only in localized areas, but also moving from one continent to the next. It seems somewhat surprising, but nonetheless, it is what it is. The data are the data. So, is the geological column reliable? Our answer to this is yes. As a paleontologist who has investigated this personally and worked on it, my own dissertation involved biostratigraphy, this very concept of using fossils to trace from one place to another in the rocks and tracing different species as we go vertically through the rock column. I observed this with mosasaurs. I observed this with ammonites, the coiled shelled squid animals. We can see this in microfossils, trilobites, all sorts of different types of organisms. So the geological column is in fact reliable. That's helpful because now it allows us to have some global benchmarks. Not every geological section has got to be interpreted only locally. We've got some pegs out there that we can hang our local geology to if we can figure out where we are in the column. So with that understood, now where and which layers of rock are we looking at for human fossils? Well, based on what we see out in the relationships of the rocks and the fossils, human fossils are found exclusively in the most recent of sediments called, the Pleistocene. Right over here. This is part of a geological unit called the Quaternary, and we can think of this very conveniently as Ice Age. Human fossils are are basically about the same as the events that were happening as the Ice Age built up and eventually melted back. We have other fossils underneath that may represent the post-flood period. I believe that they do, although there's this area of continued debate and discussion within young Earth creation community, although pretty much every young Earth creationist believes that the human fossils and the Ice Age are post-flood events. So even if we think that the end of the flood should go higher up in these Cenozoic units, and some argue that it should be high into the Miocene or into the Pliocene, everybody is in agreement that the Pleistocene human fossils are in fact post-flood. So Pleistocene, and as I said, these are post-flood. Why is it that we think that? Well, most of the locations where we see human fossils fall into two different types of categories. That is, the general types of sediments and sedimentary environments that we see them in are either near surface sedimentary and volcanic deposits. Sedimentary deposits are going to include sands, clays, gravels, things like that, lakeshore deposits and sediments, and also volcanic materials or other sediments that have a lot of volcanic material with them, volcanic ashes and the like. And these materials are very localized. They're not big, broad swaths of material that cover half of a continent. They tend to be very, very isolated patches of sedimentary material that are found within the existing, what we call geomorphology, the existing geography of the area. So you might find human fossils in lake sediments between two hills, and the lake sediments look different than the sediments on the other side of the hill because the rocks are providing material for this, and it might be different rocks providing in the next valley over. So these tend to be very isolated and small-scale geological deposits. Second place where we see a lot of human fossils, especially Neanderthals and Homo sapiens, but also some others as the weekend will play out, are in caves. And caves are very peculiar and very localized types of settings. So again, both of these are localized. They don't have widespread distribution that we expect of flood deposited sediments. For example, if we're looking at Allosaurus fossils, Stegosaurus fossils from the Morrison Formation in the American West, we can trace the Morrison Formation from Utah all the way up to the Dakotas and Montana. And that's a pretty huge area. It's covering a good chunk of the American Southwest and Central West even. Whereas the deposits that we see for something like Neanderthals are going to be within a particular valley. And that's all. They're going to be in particular caves. So Caves are interesting and important for particular reasons. Let's take a look at how these form. So the majority of caves are made within sedimentary formations made of the rock limestone. There are caves in other rocks as well, but well over 90% of the caves in the world come from limestone and dolostone. Those are two types of rocks that have carbonate as their basic mineral construction, either calcium carbonate or a calcium magnesium mixture, limestone and dolostone. That's important because carbonate minerals are able to be dissolved with acid. So when you walk into a cave, you're walking into an area that used to be solid rock, but that rock has been completely dissolved and removed through a process of acidification. So we can see down on the left over here, some images from Lenham Cave in Nevada. The cave is there because of dissolved rock. And then we have additional features that are now new precipitation of rock. So stalactites that we're looking up over here, or stalagmites from the bottom, or the connection of the two, which creates a column. These are all formed by new deposition of sediments, of limestone material inside the cave after the cave has formed. So we've got the formation of the rock, which is a singular event. We have the formation of the cave, which happens sometime later on. And then we have the types of sediments that form inside the cave after it's been formed. So later events. So again, sequences of events, relative time here, not an absolute numerical age. So as I said, limestone is made of calcium carbonate. This is a mineral that dissolves with acid. We have a picture of a particularly nice clear crystal of calcium carbonate called calcite here. It does a cool trick that I like to show with my classes called double refraction. It takes a single line, and instead of just bending it one direction, like you might see in a glass of water where a straw comes in and seems shifted from its actual position, calcium carbonate actually splits the beam of light into two units. And so you get these two fairly pale shadows of holograms, if you will, of the actual line underneath. And something like your Alka-Seltzer displays the dissolvability of calcium carbonate really well. Alka-Seltzer is made of calcium carbonate that's ground up into a paste and then turned into a little disc. And mixed in with that disc is an acid, citric acid, which is why your Alka-Seltzer tastes like Sprite. It's designed to have a lemon lime kind of flavor. When the citric acid dissolves into the water, it turns the water acidic, and the acidic water then attacks the calcite, releasing some of the medicine as it does, and all of those carbon dioxide bubbles that allow this to become a fizzy drink. So this is how calcium carbonate as the grounding material, the base material for limestone operates. Now, almost all of the limestones in which we find caves are marine deposited dolostones and limestones. They're older than the caves, as I mentioned, because the rocks themselves have to form, compress the sediment, and lithify to become stone. And then later on, there is a more recent dissolving, a dissolution, likely coming from rising hot acidic waters that are carving out these caves, dissolving them and carrying away the dissolved material as basically a kind of a salt dissolved in the water. So an example of this, where we have some hominid remains, is the Lingbua cave in Flores, Indonesia. This is the Lingbua cave. You can see a very large opening. This is a well-known cave. And in 2003, the discovery of some very small hominins were found, called Homo floresiensis. Homo floresiensis stood only about 3'4", 3'6" tall for a full-grown 30-year-old female. There are 3 skeletons of Homo floresiensis that were recovered from Lingbua. Ongoing excavations are happening there. There's been some other evidences of fires, a little hearth. There's been some processed mastodon bones, and also the mastodons are dwarfed as well. So we've got a limestone cave that must have been exposed and subsequently colonized after the flood, because the sediments inside this cave don't look like the sediments outside the cave. And we would expect that if floodwaters were rising and washing in, they would take outside material and push them into the cave in order to bury people. But instead, it seems like this was a dwelling place. People were living here. They were creating fires and cooking food. They were going out getting mastodons and preparing them or butchering them in the area, things like that. Even if it wasn't Homo floresiensis that was doing it, that somebody was doing that, and that indicates that there is time available for this. It doesn't look like this is something that is in the midst of the catastrophe of the flood. Now, these fossils were nicknamed hobbits because of their discovery in 2000, or their description in 2003. It was right around the time that the Lord of the Rings movies were immensely popular. And here you have these really short people. They picked up the nickname hobbits. Again, an adult female, just 3.5 feet tall, and only 50 to 60 pounds total when full grown. This is a very small individual, extremely small. This is about as big as my 6-year-old daughter or 5-year-old daughter at the time. Another cave where we find hominins in there, and Todd will be talking more about this in his, so I'm not going to talk too much about this, but the Rising Star Cave in South Africa, home of the discovery of Homo naledi, which has just been in the news lately for additional discoveries and interesting stuff going on there. But again, here we have a dolostone. This is made of calcium and magnesium with that carbonate. The rocks are angled at a certain angle, and you can see that the some of the cave structure follows along those layers, and then some other ones don't exactly. So they've got a rather complex cave system down here. Again, another this is one pathway down into the cave. Another pathway going out this way leads you down some other stuff over to this chute. And it was back here where the first fossils of Homo naledi were discovered. This is far back into the absolute black recesses of the cave. Animals don't live back in here. There's nothing to eat. There's nothing to see. It's frightening and scary back down here. So once you get past the cave entrance, animals and people generally don't use this stuff, but there are a whole bunch of skeletons that were found first in the Dinwiddie chamber and now in a variety of other places. This is, on the left, a schematic of a larger area of the whole cave. It's a very, very complex cave system. You can see various passageways and connectors and whatnot. But notice also somewhat of the geometric pattern to these. And a lot of this is going to be following fracture lines in the rock that allowed water to pass through and dissolve out parts of the cave. So it would seem, once again, that this is evidence of an occupation or use of this cave that was happening sometime in the past. The sediments, even within the cave, are different from one place, such as out over here, versus in here. So this was definitely blocked. Rising floodwaters didn't wash a whole bunch of things down over in here. They would have gotten deposited and plugged up far earlier on. Instead, we seem to have some purposeful deposition of bodies back over here. But again, the context here seems to be post-flood. This is the skeleton of Homo naledi as was first found. There's more material that have been found since then. I'm going to skip over that in interest of time. So when comparing these with other animal and plant fossils that are found alongside human fossils, another reason to consider that these are post-flood is that we don't find things like dinosaur fossils or trilobites along with the human remains and the hominin remains up here. Instead, we find other animals characteristic of the Pleistocene. We see Ice Age types of mammals, not always the ones from North America, for example. We're looking at places in Africa, places in Europe, and their species are different. So don't expect a woolly mammoth with stuff in South Africa. But nonetheless, Pleistocene organisms are found alongside them: antelope, deer, bison, elephants, etc. And all of this seems to be consistent with things that are up in the Pleistocene, not any sort of admixture of materials of what we would consider to be flood fossils. So our Ice Age is up over here, our human fossils are up over here. That helps to answer these first three questions. Is the geological column reliable? Yes, as a matter of fact, it is. Human fossils and the other hominid remains are found in the Pleistocene, and we seem to think, for good reasons, in fact, quite a number of reasons, that these are post-flood. The next part then is actually going to be pretty easy as we take a look at our geography. Where are these human fossils found in the world? Well, what locations and what was world geography at the time? So looking at world geography right now, we can take a look at where human fossils are found. Well, I haven't talked about many of these different species in particular. Todd will be doing a good bit more of this later on, but Homo erectus is fairly widespread, found in Africa, the Near East, and the Far East, all the way down to places like Indonesia. The type locality for Homo erectus, in fact, was on the island of Java, and Homo erectus, or very similar considered equivalent groups, have been found in the Far East, in the area around the Middle East of the Middle East and far Eastern Europe, and known as Homo ergaster, but considered the same as Homo erectus in Africa. This, on the conventional time scale, would be about 1.8 million years ago, but would be within the Pleistocene, the beginning of the Ice Age. Homo naledi is a good deal younger than that, about the same age, and in fact younger in some cases than some of the others. Neanderthals are found actually before and alongside, at least in terms of time, Homo naledi. They persist longer than Homo naledi, which is so far only found in those caves in Africa. Homo floresiensis, the hobbit, is coming in fairly late on the conventional timescale, 60-ish thousand years to maybe 100, but still we're talking about later in the Ice Age. Neanderthals and an enigmatic group called Denisovans, they're coming in after that, and coming in most recently is Homo sapiens, or almost most recently. Homo floresiensis is also recent. We've got Homo sapiens found first in Africa before they are found pretty much everywhere else in the world. So when we're interested in human origins questions, when we're talking with an evolutionist friend, for example, we're going to be talking about fossils of the old world. Humans don't come over into the new world until the very end of the Ice Age, at the peak distance and extent of the glaciers, which allows a whole lot of interconnection between the continents that previously was not available. So here's a geographic map that shows what the world would have looked like at about the time of the greatest extent of the glaciers. The age on conventional time shown here, 50 to 18,000 years ago. Ka means thousands of years ago. So during the peak of the Ice Age, when the ice sheets were at their greatest expanse, world geography looks about the same, except it's a little different. The continents aren't in any different position. They've only shifted a few feet or a couple of miles at the most from this. But take a look at Florida. It's kind of enormous. The Yucatan Peninsula is larger still, and there's this other projection coming off of Central America. In fact, all of South America looks kind of thicker, and so does, wow, Indonesia is actually completely confluent with Asia, and the island off the coast of India is connected over there. We have a number of areas that are far more extensive. Australia is connected up with the Philippines. So we can see that at the peak time of the glaciers, there was a lot more land mass that was extended over this area, and that is because of the way that glaciers operate. Also, if we take a look from the top, we can see that the glaciers pretty much create a circle around the northern hemisphere, but don't extend all the way down to even where I'm living in Lynchburg, Virginia. When we think of the Ice Age, sometimes we're tempted to think that the entire world was covered in ice, and that certainly wasn't the case. If you lived in the equatorial regions, it was still hot and humid. It was plenty hot and humid in the equatorial regions. It might be slightly cooler than it is today by a couple of degrees, but that's about it. However, if you were living in Europe, you were right along the border and the edge of the massive great glaciation, and you had these big glaciers coming off of the Alps as well. You can notice lots of glaciers in the Himalayas. So was there really an ice age? Yeah, there was. And the ice age is a late post-flood event. Continental glaciers, that is, glaciers covering large sections of continents, were covering over portions of North America and Greenland, as well as large sections of Northern Europe, parts of Asia, and of course, Antarctica, which likewise was completely glaciated as it still is today. So how did the ice age happen? Well, we believe that after the flood, the energy from the flood created very warm ocean waters, which evaporated substantially and caused a lot of precipitation. That precipitation helped to cool the oceans over time, but they would keep pumping out heat until much of that precipitation would come down as snow and ice, particularly in the northern and southern polar regions once they started cooling down. As more and more snow fell in the continental interiors, in the polar areas, than could melt, it led to a buildup of glaciers. So you have a net build of snow and ice making glaciers if there is more snowfall each year than there is melt that happens during the summer. And as a result, you end up with ice sheets that flow from high points of elevation towards low points of elevation. And that's because as the snow is building up, it's creating literally a mountain of ice. And that mountain of ice will spread out and flow in all directions. So we have a tendency to thinking from north to south, but the reason that this is the direction that the glaciers generally flow here is because to the north is where the glaciers are really, really thick, and towards the south, towards me, for example, is where the glaciers aren't. And so they progressively thin, and that creates a gravitational flow out towards the south. Now, on other areas, the glacial flow might be towards the north a little bit, so it depends on where you are. So glaciers always flow in one direction from points of high elevation towards points of low elevation. This is why mountain glaciers flow from the mountain peaks down through mountain valleys that they are actively carving, and eventually you get to the point where they are melting, and this is called the terminus. Now, if more snow gets built up and more glacier gets built up than melts at the terminus, then the glacier terminus moves forward. The glacier is always flowing forward, but the terminus also advances if there's a net addition. If, on the other hand, temperatures are warm and the terminus melts very quickly, the glacier's terminus will move uphill, but the glacier itself is still flowing downhill. And I basically just said that all right over here. So as glaciers grew in the continents, sea level fell because what we're doing is taking ocean water and trapping it as giant ice cubes on the land. We're transporting that ocean water onto the land and storing it. And so eventually we start dropping down the level of the oceans. The elevation of the ocean is lowering as all of this water is being put on the continents. Sea level was lower by 400 vertical feet compared to where it is today. And that is why those coastlines during glacial maximum were so much more expansive than they are today. If I want to go to the beach, I can get in my car and in 4 hours I can be at Virginia Beach. But it would take me another hour driving at 60 miles an hour probably to reach the end of North America's land during the peak of the Ice Age. Now, like I said, not all locations experience cold and ice. Most of the world, in fact, was ice-free. Temperatures were globally cooler, but places were still pretty hot. You still had deserts in some areas, for example. Still would have deserts in places like the Sahara, although the Sahara was better watered because you did have cooler temperatures, and the glaciers would have created some slight variations in the overall flow of the ocean currents that could bring more water into this area. Now, migrating people over to the United States, or it is the United States, to North and South America, required them to cross over a land bridge that we call Beringia. It's in the Bering Strait today. This would bring over animals like mammoths and mastodons, saber-toothed tigers, bison. We think of the bison as a North American mammal. It's not. It just got here before Europeans did. The North American bison is an Asiatic immigrant, and it was people eventually that would follow these migrating animals across the Bering Strait, but as land, Beringia. And they would then come to colonize North and South America as the first peoples. And as they did, something interesting happened. As people from Africa, Homo sapiens from Africa migrated out, they met up with Neanderthals and Denisovans and interbred with them, creating hybrids. And as they left then, they carried those hybrid genes with them out into Asia and out into places like North and South America eventually. And so all of us who are of Eurasian descent, anybody who came through this region here where Homo sapiens met up with Neanderthals, carries genes for Neanderthals and very likely Denisovans as well. Some populations, very high amounts of Denisovans. If, however, your population never left southern Africa, then you probably have very, very little Neanderthal. The only Neanderthal genes you would have would be backfill coming in from others who had met up with the Neanderthals. The Neanderthal people did not live in Africa ever, as far as we can tell. So the Ice Age ended, but massive glaciers still persist over Greenland and Antarctica, and global temperatures today are cooler than they were early in the post-flood world, and cooler than they were probably in the pre-flood world. They're a little bit warmer than they were during the peak of the Ice Age as we have melted out. And I would think that the climate is much more stable now, certainly, than it was during most of the post-flood period, as the Earth is reeling from the effects of the flood, and the continents are still adjusting. We have lots of volcanic activity that is eventually dying down as the process of plate tectonics grinds to a slower and slower pace. And we benefit now from having a climate that is less chaotic than it was probably, especially right after the flood. So we now find that our human fossils, of which we're interested in for, say, human origins, are found in the old world of Africa, Asia, and Europe. World geography looked very much like today, but it was becoming icier and was eventually much more interconnected before the glaciers eventually melted out, rose sea levels, and broke off some of those connections. The Bering Strait is no longer passable by foot. You have to get in a boat to get across it. You can't walk your way from Indonesia over to Asia. You've got to get on boats, and Australia is disconnected from everything, whereas that was not the case before. So with that, we can get a sense now of where our human fossils are that are going to be discussed over the next couple of talks. And thank you all very much for your time and attention. May we do what we do here for God's glory so that others may hear of his great goodness, and hopefully that we can provide some context and answers for questions when they come up. Thank you, and Lord bless.
Thank you, Dr. Ross. Really appreciate the information that you're sharing. Participants, if you have a question, feel free to put it into the Q&A area of Zoom there. While we're waiting, maybe I can start off some questions if you don't mind.
Sounds great.
First of all, is there, like most presentations, there's probably something important that you wanted to say that you didn't get to say. Is there anything you'd like to share in additional?
No, actually, thankfully I was able to get through most of this. This is a talk that I had practiced a good bit. The talk tomorrow, ask me that again, because I'm probably going to have to move through a few things that I know I'm going to miss. But I think, you know, one of the important take homes, and why I spent a good bit of time at the beginning talking about the geological column, is that there's a tendency to think that the column itself is a product of evolutionary thought. And that it's just something that the evolutionists use in order to prove themselves, that it's circular argumentation. The fossils are used to date the rocks, and the rocks are used to date the fossils, right? It's a very common argument that was used a lot in young Earth creation writing, and it's one that's quite mistaken. And as a creationist and a paleontologist, I had to come to terms with the recognition that that wasn't the case as I studied the very topic of biostratigraphy, that is the justification for the column itself. And there were some situations in some places where I looked at the correlations and go, yeah, I don't know, there could be some difference in time. You're saying these are happening at the same, but not really so sure. But the number of times that I came across that was rather minimal. And instead, I saw from my own experience, as I mentioned, looking at mosasaurs, ammonites, microfossils, trilobites, and even dinosaurs and other sorts of critters, that these patterns hold up, and they hold up well. So it's okay to look at the column. You can think of that is the data. That is God's revelation to us through the natural world. And we have different interpretations of that. We have interpretations from an ancient Earth perspective. We have interpretations from a young Earth perspective. And hopefully our interpretation will eventually see the greatest success as a scientific construct.
Excellent. I have a couple questions, a couple that were sent to Joel directly. Is it true the only place the complete geologic column appears is in geology textbooks?
No, although I can understand why. Most places that we go to, we see very little of the geological column. Here in Virginia, where I live, I'm in Precambrian material. And so we're talking about stuff that was down low on the column, and there's a lot of it, but I don't have any of the fossiliferous rocks that I think are part of the flood here where I live in Virginia. Now, if I go over the Blue Ridge Mountains and into the Ridge and Valley province, then I start getting into the flood rocks, and I can trace those as I go higher and higher, and I can hit Cambrian and Ordovician and Silurian rocks. And if I keep going into the Appalachian Highlands, then I can eventually make my way up into the Mississippian and the Pennsylvanian rocks. But that's as high as I can get around here if I'm going in sequence. There's a few other places where I can go to see some Triassic and Cretaceous stuff, but I've got to kind of pick around to find it. But there are a few places where the geological column is effectively complete. My master's program was in South Dakota, out in the Black Hills, and we had every single unit of the geological column of the fossil stuff, Cambrian through to present, with one exception. The Silurian was not there. There's a big erosional mark. So it's not like the Silurian was missing and found somewhere else. It was missing in the place where you'd expect it to be, right? It's supposed to be here. There's an erosion line, but I've got Cambrian and I've got Ordovician, and then Silurian's missing. I go straight into Devonian. And that's a common situation out throughout the American West. The Silurian is very thin or missing because of erosion that happened over there. However, if you get up into the Williston Basin of North Dakota and you drill down, you'll be able to pick up small bits of that. So you can get everything in the Williston Basin. The reason why we don't have everything everywhere, or even everything in even very many places, is because in order for a place to represent the entirety of the geological column, or at least have representation of all the units, it would have to be a consistent low spot all the time to constantly get sediments to fall in. It would have to keep sinking, keep being a low spot, so more and more stuff would pile on. And then eventually it would all have to be lifted up to a point where we could observe it or drill down through it. So anytime you get a point where it stops sinking and goes up, you can erode and lose something. And then maybe it sinks down, you start putting something new. And like that Silurian is missing because there was a lift up, an erosion, and then more deposition. So in order to get the entirety of the geological column, you need something to be a low spot for the entire flood and pretty much all of the post-flood period as well. And so that's why you don't see that. Instead, we have local, in fact, the surface of the world that you and I are living on right now is an unconformity. It is a break in the rock record that is showing erosion because we're walking around on soil and not, deposition rock.
Another question is, would we expect earthquakes to be milder in the future post-flood?
I think so. And I believe Steve Austin has a paper from a good number of years ago, back in the late 80s or early 90s, where he was looking at earthquake intensity over time. And I believe that he saw a trend line of decreasing intensity. That doesn't mean that we couldn't have huge earthquakes at any given time. We certainly do. Many of us remember the earthquake that struck Japan back in 2011, damaged the Fukushima Daiichi nuclear power plant. That set off some other major earthquakes later on around the Pacific Rim. 2 other large ones happened within the next 2 years, probably as a result of release of strain. So as the continents had moved during the flood, they've still built up an enormous amount of strain, and they're releasing that every once in a while. So we can still have large earthquakes, but I would expect on average, we would probably see less over time.
Next question. Why or how is it kangaroos are localized in the area of Australia?
That is a very good question. Kangaroos and a wide variety of other types of animals. So the entire Australian biota is radically different from everything else that's there and in New Zealand, right? Those are the 2 places. And I believe that Australia was reached by marsupials probably very early in the post-flood period, and possibly not through the path that we often think. We tend to think of the way to get to Australia is to go through Asia and cut down through Indonesia and the Philippines. And that's certainly the way that, say, the Aboriginal Australians did. That would have been their path during glacial maximum. They couldn't walk there. They did have to get over by boat, but they could get a good long distance from Asia and then hop over a couple of islands and eventually get to the mainland. But when they got there were already kangaroos and wallabies and wombats and, Tasmanian tigers, all sorts of different things. And those animals may have gone through a more southerly route where South America, Antarctica, and Australia were actually connected to one another, and to possibly to Africa. So some of us in Young Earth Creationism, Chad Arment, Matt McLean, and myself are pondering the idea of a possible southern route for some of the marsupials that get into those areas, because we also know, for example, that South America had a significant amount of marsupials in the Cenozoic fossil record, and it wasn't until South America connected with North America not long before the Ice Age began, and that created a flood of migration between those 2 continents. And North American mammals went down to South America and kicked the tar out of a lot of the marsupials that were there, and so all the South American jungle cats are actually North American migrants that went down there. And we got armadillos out of the deal. We got giant ground sloths for a while. They came up from South America into North America. That was one of the first major fossils discovered in what was Virginia, what's now West Virginia. Thomas Jefferson actually did a bit of a fossil description. He did some paleontology and described Megalonyx, which was a ground sloth the size of a black bear. Pretty sizable animal, but down in South America, they have ones that would have stood almost 17 feet tall. Pretty amazing. So there has been interchanges and faunal migration between North and South America, and the faunas of both continents changed out of that. Australia was locked away as its own thing. So we think there might have been this southern route that brought marsupials to these southern continents. And only when they finally rafted against others, like Africa rafting up against Europe and Asia, then there's this flood of placental mammals that come in and overtake the area and are just competitionally better, it seems, in a number of different ways.
Next question. If the flood had not happened, what would the geologic column look like?
Oh my, if the flood had not happened, we certainly wouldn't have the geological column as it exists. Because if the geological column is largely a representation of the sequential burial and destruction of ecosystems as the floodwaters rise first and inundate the oceanic environments and then pile into the continents as well, if the flood never happened, then we would have whatever sedimentary materials happened during creation week, and whatever the continental configuration was at the end of creation week, our continents would not be where they are today. They started off someplace different. And our major models for how the flood occurred involve massive amounts of lateral movements and collisions and mountain building and splitting in order to make North America. North America at the end of creation week was probably about 90 degrees sideways, and Virginia was in the southern tropics. So, I'm in a very different locale because of the flood compared to where my state was at the beginning of the flood. So we wouldn't have anything like the geological column at all. We would have a lot of loose sediment and creation week material and post-creation week material, and it would be a much thinner deposit of sediment and rock, if we'd even have much for rock at all.
Good. Next question. If God created humans in his image and all of us came from Adam and Eve, how can there have been different species of humans like Neanderthal?
That's a really good question. And yes, I did refer to Neanderthals as different species than us, and Homo naledi is given a different species, Floresiensis is given a different species name. Now, in paleontology, we don't usually have the luxury of doing mating experiments with our fossils, right? You put 2 trilobites in the drawer and play some soft music for them. You come back the next day, there's still just 2 trilobites, right? If anything else has happened, let me know. That's a problem. So we have to describe species on the basis of their physical forms only. And so the description of Neanderthals is based on the physical materials of the fossils. And we see a consistent physical form in these groups that is somewhat different from ours. Not tremendously different, but certainly somewhat different. They don't have a tall forehead like you and I have. Mine's exposed a little bit further as we go back, right? But they have a sloping forehead that is much lower down. They have a thicker brow ridge here, and their mouth is a little bit more protrusive. Not terribly so, but still kind of feels like, I think Todd Woody once said it, like kind of somebody grabbed in their nose and just pulled out a little bit. And their body form is a little bit different. They're more robust than we are, generally speaking. I would tell my students that they're the middle linebackers of the human group, and we are we're the tight end of this. So we're slimmer. And so we've got these different fossil forms out there, and they seem to be consistent enough that we can name them as a thing. We can name this as a group. We don't see Homo naledi shifting into our physical form. It's not like this big jumble and we have no idea. So I think calling them different species, first off, from a pragmatic standpoint, is very, very helpful, because it helps us say that's this group. We're talking about these fossils that are different from these other ones. We're treating the fossils like we would treat other fossils. Now, to the question of, if we're all made in the image of God, why do we have these different forms of humans? And I think the ones that I've been talking about are in fact human. Well, in the post-flood world, we see lots of different species happen from different kinds. Today, we have about 60 different cat species in the world, and we, as young Earth creationists, almost all creationists, believe that Noah brought on a pair of cats. Maybe at most 2 or 3, but pretty much all the cats that we have come from a pair. And that's a lot of species. That's even different genera of cats. But they are cats, and they're a part of the same kind. We are humankind. God doesn't refer to us as a kind, but we still refer to ourselves as humankind. Why should we not have the same sort of capacities in the post-flood world for differentiation of our physical form that are highly adapted and programmed by God to be adaptable to the environments we find ourselves in? And so it doesn't mean that they're not human and we are, or they're less human and we're more human, or we're less human and they're more human. It simply means that we've got different populations of people that went out, and their physical forms shifted and changed and altered. And when people start looking a little different from other people, they tend to separate from one another a good bit, and that could have a compounding effect on the morphologies of these. So one human family, one kind, we can still refer to them as species, even though we also know that we did interbreed with some of them. We know that we interbred with Neanderthals. We know that we interbred with Denisovans. We know that we have genes in our bodies that we get from them. And, so there was compatibility between those things. And I think people see people, and sometimes they want to make more people when they meet up together. And it seems to have happened consistently enough that this wasn't accidental. This was at least some type of occasional or continuing type of activity. So all of them, human beings, different physical forms.
Great. Next question. What is your take on the idea that hominids found that appear to be more primitive are actually humans affected by either isolation or inbreeding?
That's a very good question and a good follow-up to the one that you just asked. I think there's a tendency for us to think that we are since we're made in the image of God and we're the ones talking about it, then we must have been the particular physical form that goes all the way back to Adam. Right? Every picture that you've ever seen of Adam or of Noah looks like Homo sapiens. It doesn't look like any of these other forms. And there's been a long history of looking at the other forms as being these aberrant morphologies, these aberrant groups that were isolated and inbred and whatnot. But I don't see inbreeding producing a consistent physical form to make Neanderthals. That's not what happens. Inbreeding doesn't do that. Isolation itself doesn't do that. And the Neanderthal population is widespread, even if their populations are fairly small within it. There's a lot of distance between them. They're found everywhere from Central Asia all the way to Spain. And they're found from the northern regions of the ice sheet. So wherever the ice was, Neanderthals got about that high to the north, all the way down to Israel. We've got Neanderthal skeletons in Israel. So that's an enormous geographic range to see fairly consistent physical form. I don't believe that there's inbreeding that could possibly be the reason for that. Then you've got the physical form of Homo erectus, which likewise, that's even a wider range going from Africa all the way to Indonesia. And so I don't think that these are the result of inbreeding. This isn't the result of isolation. Isolation can lock in certain traits, but I don't think that it's the sort of thing that turns someone like us with, say, a 1,300 cubic centimeter cranium into a Homo erectus with a 1,000 or a 600 cubic centimeter cranium. It doesn't turn us into the dwarfs of the hobbits, of Homo floresiensis, or a new one that was found, Homo luzonensis. Something else was going on there. Isolation was important for them, and dwarfing happens from them, but I don't think you go from our physical form to that one. I think it's actually much easier to go from a physical form like Homo erectus into these others. I can see getting from Homo erectus to Homo sapiens a lot easier than going from Homo sapiens to Homo erectus and to Neanderthal and to all these other things. So in the end, I don't think Noah looked very much like us as the species. I think Noah probably looked much more like a Homo erectus. Could have been something else. I'm certainly open to the options, but I also want us to think for a moment that we don't want to take the present and push it into the past, right? That's a cardinal mistake that geologists have made, but we also have a tendency to be a bit vain about it and to see ourselves like everybody else in the Bible, right? We know what Adam looks like. I've seen the Sistine Chapel. He's a white guy, so probably not, probably different.
Very interesting. Next question. When speaking of, quote, native North and South American, end quote, animals, as opposed to those that migrated from Asia, like the bison, how do we think they got there after leaving the Ark?
Very good question. Well, the bison and the saber-toothed tigers and whatnot, they came over about the same time as the Native American, or what would become the Native Americans did, really Mongolians came over following all of these herds. Now, there were other animals that were there earlier as well. We've got a rich fossil history in the Cenozoic, and there were periodic connections between North America and Asia and North America and Europe. Both creationists and evolutionists have to recognize that fact because we see European mammals that show up in North America and North American mammals lower down that show up in Europe a little higher up. So it seems like there's cross movement throughout the Cenozoic on some sort of episodic periodic basis. So it appears that there were additional land bridges and connections. Early on after the flood, North America and Europe were much closer to one another. So I expect that there was a lot of migration going up through that corridor. And only later on did North America move far enough that the Asiatic side comes in from the other end and connects them. So those are some of the ways that they get there. There are additional land bridges to consider besides just the Bering Strait, particularly as we consider the continents still drifting away from one another, starting off closer in the early post-flood world. We get a lot of movement over. Then we have kind of a North American established group that's different than for when the Asiatic groups come over and become the North American animals.
Final question that's more of a comment. Matthew 24:7, for nation will rise against nation and kingdom against kingdom. There will be famines and earthquakes in various places. The comment is, this seems to indicate the earthquakes will increase as we approach the end of the world. Comment?
Yeah, I don't think that they will necessarily increase. One of the things that we have to remember about the passage here in Matthew, which is a really important one, obviously, Jesus is talking about his ultimate return, that there will be earthquakes. And if you understand the context of where Jesus is living in Palestine, this makes some sense of the area. Mount of Olives is right next to a large fault line called the Transjordan Valley, right? The Transjordan Valley, and why you have the Jordan River and the Sea of Galilee and then the Dead Sea. Why are those even there? The Mediterranean's right over to the west, and none of those rivers flow that way. Well, they're stuck in a valley that is moving because of a fault like this, and also separating out a little bit. So earthquakes are relatively frequent in Jesus's time and in Jesus's place, as were wars and rumors of wars. You have to remember the War of the Zealots that was completely crushed. You have to remember the war against the Greeks led by the Maccabees before that was short, right? The Roman occupation and the oppression there. There will be wars and rumors of wars in diverse places. There will be earthquakes. Jesus had said that it would be like the days of Noah, where people were marrying and giving into marriage and eating and drinking, right? In a sense, Jesus is saying that life will be continuing as it usually does. And then people who will not see the signs will be surprised at the return. I think a little bit of our perspective on reading that passage and thinking there's going to be earthquakes all over the place, they're going to be huge, is because of our own theological history rooted in Western Europe and Eastern North America, which geologically are extraordinarily quiet areas that don't experience earthquakes. And because of the development of Christian thought in these areas, we don't think of earthquakes as events that occasionally plague us. We think of them as absolute disasters that, don't happen. But in Jesus's time, I just remember there was an earthquake at the time of the crucifixion, and there was a aftershock when he rose. And Steve Austin has believed actually that he's found the actual disturbances in the lake sediments in the Dead Sea that show the crucifixion earthquake. And he's found also the earthquake that happened at the time of Hezekiah, which is written about in the book of Amos. And that's a huge one. That was a magnitude 8 point some odd that rocked the Middle East, destroyed all sorts of stuff. It was talked about for hundreds of years. So again, Jesus is talking about this and giving context. And I think if we think about the context in which he was living and the angst and the concern and the wars and all the things that were happening at that time, the propensity for earthquakes, it puts a little damper on us thinking that the whole world is just going to be roiled at the time. Right now, there are wars and rumors of wars in our world right now, and there are earthquakes in diverse places. Jesus can come at any moment.
Absolutely. Thank you so much, Dr. Ross. I appreciate that. Attendees,